Good morning, everybody. I'm back and we are on a little ride to see the sights today.
While I'm on my way to an appointment I have, I want to talk about something that came up recently. I was talking to a developer and we were discussing the changes that were made to S3 by AWS. So if you haven't heard of it yet, AWS has introduced S3 Read-After-Write Consistency across the board for all operations, including metadata operations, which is something that is basically a first in the industry. And then the first thing that comes up is, but Google Cloud Storage had read-after-write consistency. True, for most operations, but not all. Some operations in Google Cloud Storage are still eventually consistent, right? It's to do with some metadata operations. I'm not going to go too much into detail at this point. However, AWS says now all our operations are read-after-write consistent. So then the developer, this person is a very, very strong, probably stronger on S3 than I am in the development side, right? In the actual use cases and how many applications they've developed for cloud storage solutions, not just S3. Most of their work is AWS, most of their work is, through the SDK. It's a Python person. So they know their stuff, right? But the question came up, so why is read-after-write even, so important? Why do you want to have read-after-write consistency at all? So, yeah, that's a really good question, because most of the services that you use inside a cloud storage, Jesus, some people are really, really like, can I not drive safe, please? Can I not drive the speed limit? I think he's going to be overtaking me. All right, let's see if he overtakes me in the school zone. Oh my God. Anyway, as I was saying, when we talk about read-after-write consistency, why would you even use it on an object storage platform? An object storage platform is used for large files, large amounts of files, just dumping your data, which is going to be read at some point in the future, probably. Not at, immediate times. It's not going to be read immediately after it's written. So when we talk about read-after-write consistency, why would we need to even have it in an environment like S3? Well, it turns out that object storage is being used more like a file system lately with lots of different kind of solutions, especially solutions that, use lots of data, like any kind of analytics platforms, any kind of machine learning platforms. They kind of expect, their object storage to operate more like a file system than anything else. So if it's operating more like a file system, then we're talking about, we need to have read-after-write consistency. We can't just let replication happen and just, wait for replication to complete. We need to be able to get that file immediately after it was written, or get that object or piece of data or data blob or whatever we're looking for. So it's really more of we want to use this object storage as a file system that is pushing the move towards read-after-write consistency, and not so much the actual requirement of object storage to be read-after-write consistent. Okay, so what is read-after-write consistency at all?
Read-after-write consistency is essentially having files or objects or pieces of data being written to a distributed platform, and then whichever backend is responsible for this platform will have the most up-to-date version of that file and of its metadata and everything connected to that file or object. In traditional systems, we're looking at eventual consistency because you want to maintain availability, because you are under the influence of the CAP theorem, right? The CAP theorem really dictates how you store data in a distributed system. And the CAP theorem talks about consistency, availability, and partition tolerance, CAP, right? CAP. Consistency means I want to maintain all the files across my distributed system consistent at all times. Availability means I want to maintain them available across all systems at all times. And then partition tolerance means I want to have multiple copies, or I want to have some kind of parity calculated and stored somewhere else, so that if I lose one partition, I can recover that partition from another physical location, right? So CAP theorem typically applies to, let's say, 3 systems that have 3 replicas. So if I have 3 pieces of data where I've written, a word like sunshine, right? And I keep retrieving that word out of that system, I'll go to the 3 backends and I'll always retrieve sunshine. So at this point, I'm consistent. right? I'm available because I have 3 different locations where I can pull this from, and I have partition tolerance because, you know, one of them can fail or be corrupted and I can still recover it pretty easily. So what happens if I change Sunshine to Rain? Well, I have to connect to one of the backends, and when I connect to one of the backends, I change Sunshine to Rain, and now at that point in time, I have to choose between consistency availability. Because I can't sacrifice partition tolerance, I need to either lock the file, replicate it, and once it's replicated, make it available again, or I need to just leave it available and sacrifice consistency. And then here you usually have eventual consistency at play, because at some point in time there will be the replication, and the replication will replicate the file across the 3 platforms. And when it replicates across the 3 platforms, then you will have 3 copies that are again consistent, right? Within seconds, replication will happen, and then Sunshine will turn to Rain on all the 3 platforms. And then once I retrieve it, I get Rain out of the 3. But while the consistency window is still active, if I make the data available, I will have inconsistent data. Platform number 1 will have Rain, platform number 2 will still have Sunshine, platform number 3 maybe got replicated and will have Rain already, right? You can't really know. So read-after-write consistency is essentially ensuring that replication happens as soon as the write is completed. So what is probably happening in that situation is, when the write to that object is coming in, the object is virtually locked. Virtually locked means you are retrieving the previous version while the write is happening, and you're making the file available. But as soon as the write completes, you put a small tiny lock on that file, replicate it or replace it with the new version, with the new copy of that file, right, with whatever you've uploaded, and then you instantly make it available. And because you've replicated in the background while allowing the previous version of the file to still be available, you have, you know, instantly replaced it, and it's instantly available for read-after-write consistency. As soon as you write it, it's replicated already in the backend, right? And you can only achieve that by having some kind of versioning in the background, where you allow the old version to exist and you don't physically overwrite that old version. You just manage the access to the old version. While the write is happening, the old version is available on the other platforms, and then as soon as the write is complete, you also replicate at the same time and then make that new version available. You make the quick switch to that new version, right? It sounds like a simple feature, but it's quite a heavy process technologically, right? It takes quite a bit of effort to actually achieve that. It's not a simple solution. So kudos to the S3 team to you know, the efforts that they've put into the platform to make everything to get off of eventual consistency, to make everything read-after-write consistent. Definitely we appreciate the effort. And where it really makes a difference now is, as I said before, in applications where you consume lots of data and you want to, you know, quickly feed from one system to another. Let's say I have an analytics platform, and my analytics platform has lots of different input files, and those input files are fed into my input analytics process. And then from my input analytics process, I do my ETL, I do my transformations and calculations and analytics processes, and then I write to S3. And as soon as I'm writing to S3, I can feed another process in the other side, because we are read-after-write consistent. So I can technically now use S3 as if it's file storage, right? I can use it as how we would usually use something like EFS, right? We usually use EFS in those kinds of time-sensitive situations. So EFS is a distributed elastic file system. It is based on an NFS protocol, right? So you can run any NFS, any operating system that will be able to read or write to and from NFS. And you always have consistency because it's a file system, right? It's not an object storage system. But I mean, having that capability on S3, it's super valuable, because S3 is like 10 times cheaper. Rule of thumb here, don't take my word for it, calculate it yourself for your use case, but rule of thumb, S3 turns out to be like 10 times cheaper compared to a file system, if you're not hitting it with too many concurrent put and get requests, right? So it always depends on, like, the storage itself is cheap, but then you've got put and get requests, and then at some point it starts becoming more and more and more expensive when you have millions upon, actually like billions of requests per month, right? Then it starts getting close to EFS territory. So I'm not saying that there is no use for EFS. There definitely is use for EFS. There definitely is use for FSX, for Lustre, right? That's a very high performance file system. It runs Lustre FS, and that will give you like amazing performance. We're talking about potentially hundreds of thousands or even millions of IOPS out of that platform, which is something that you just can't do with traditional file systems, right? So it is really, really powerful, and for some types of analytics jobs or for some types of operations, that's your best option there. All right, I'm at my destination, so this is where I'm going to leave this one. I think that read-after-write consistency is great for some purposes, and I think that we'll be replacing a lot of file systems in a lot of applications with S3 directly, because now that you don't have the limitation of how eventual consistency sort of limited our application in some senses, we're now doing a lot of projects where we're considering using S3 as our main file store. And does this signal the death of the file system? No, as I said, like, there are some situations where object storage is going to be more expensive because of frequent reads and writes. There are definitely situations where you need a lot of IO operations per second, especially some kind of HPC or medical or weather simulations or things like that, where it's a big data set and you need to do lots of reads and writes per second, millions of reads and writes per second. That's where file systems are still, still king. However, lots of your run-of-the-mill things that are sitting on file system right now, I think are ready for, definitely ready for S3. That's where I'm going to leave it. So thank you very much for watching. If you find my videos interesting, please do consider subscribing. I will have lots more of these coming up throughout the summer as well, throughout the spring and summer here. And then yeah, look for some more demos. Last week I just released the particle SQL on DynamoDB, which was really cool. And yeah, that's all I'm gonna say. Thank you very much. Bye.